Welcome to Numerical Solutions for Chapter 10 Wave Optics for Class 12 Physics NCERT. Here is the first question. Monochromatic light of wavelength 589 nanometer is incident from air on a water surface. The question is to find the wavelength, frequency, and the speed of the reflected as well as the refracted light. The refractive index is also given. So we know that for a reflected light, the wavelength and frequency are not going to be different. So we calculate as it is. The wavelength is given, speed of light is given. So you calculate frequency using the expression V over lambda. So we have the solution. And for the refracted light, this velocity is going to be different because there is a refractive index. So we use the expression V equal to C over N and we find the velocity. And once you find the velocity, you can go back and find the wavelength as V over F. Moving on to question number 2. The question asks you to identify the shape of different wavefronts for a light diverging from a point source emerging out of a convex lens and the portion of wavefront from a distant star. So how does it look like? So diverging means it's a diverging spherical wavefront, and out of the convex lens, what happens? The diverged wavefront is getting, once it is through the lens, it becomes a plane wavefront, so it gets modified. And what happens when it is from a distant star? After a very long distance, this happens to be a plane wavefront as you see it in the figure. 10.3. So the question asks you to find the speed of light similar to the question 1 and ask you some qualitative question. Is it independent of the color of light? If not, which of the two colors, red and light, travels slower in glass prism? So we calculate the velocity as we did before. So this is and also the wavelength. And moving on to the question of whether it is independent of the color of light, and it depends on the wavelength. So the refractive index for violet light is more than that of red. Hence, the violet light travels slower than the red light. So that is the conclusion. Now this question is based on Young's double slit interference. The slit separation is given, slit screen distance is given, and the distance between the central bright fringe and fourth bright fringe is also given. We need to calculate the wavelength of light used in the experiment. So fringe width is to be calculated. So given the width of 4 fringes, you need to calculate what is the fringe width. So this you do. And then slit separation and slit screen distance. Then you substitute for the to calculate lambda. So only calculation here is to find out what is the fringe width. Other things are given directly. Moving on, we need to find the intensity of light at a point on the screen where the path difference is lambda by 3, where the intensity where the path difference is lambda is given. So how are we going to solve it? We use the expression for intensity, I equal to 4I0 cos square phi over 2. But here we have to change phi, the phase difference, into path difference. So we do it for lambda and we also do it for lambda by 3. So calculate for lambda, let's say this is I1 and which is given, which is k. So once you substitute, you understand for I0 is equal to k. So we are going to use this information to calculate what is the intensity when the path difference is lambda over 3. So I2 is equal to, go by the same method, where we have to calculate the new phase difference, which is using the path difference lambda by 3, and then you substitute, find the cos square value, then you get k over 4. So here again, based on Young's double slit experiment, we have to find the distance of the third bright fringe on the screen from the central maximum, and also the least distance from the central maximum where both the fringes coincide. So we use the distance expression for the nth bright fringe, x equal to n d lambda over d, or x is equal to n times beta. So you get the expression and then you substitute. And then where does it coincide? So how do we do that? We assume nth fringe coincide with the n plus 1th fringe, and then we solve for n. So once you obtain what is n, we again go back and find the distance using the expression x. Now this question is to find out the angular divergence. So what is given is the angular width in air. We need to find out the angular width when you immerse the entire setup in water. So we use the approximation here. Theta is equal to here the fringe width beta divided by d. So fringe width is very small, so we can take this distance to be still equal to d, and then calculate what is d, small d, or we can also use the equation for d in the second expression, where theta is dash is equal to beta dash by d. So substitute and then substitute for d, which is lambda by theta, and lambda is equal to mu lambda dash, cancel dash, lambda dash, and then you get the answer 0.15 degree. This is a straightforward and simple question to find the Brewster angle. So mu equal to tan IB, and what is IB? So tan inverse the refractive index. And here this question is to find out what is the angle of incidence when the reflected light is normal to the incident light, and also the wavelength and frequency, which is similar to question 1. So we use the expression that we used in question 1 to find the frequency, which is V over lambda, which is 3 times 10 to the power 8 over the wavelength, which is given in angstrom, change it to meter, then you get the answer in hertz. And then what angle of incidence is the reflected ray normal to the incident ray? At 45 degrees. So they are separated by 90 degrees. So here comes the last question. So at what distance ray optics is a good approximation? So we go back to our Fresnel calculations, where it is given as Fresnel distance, where within the distance where the ray optics is valid, a square over lambda. So we substitute, we get the answer as 40 meters. So we have discussed 10 questions in chapter 10. If you like the solutions and if you like the presentation, please like our channel. Thank you very much.